Good morning, everyone. My name is Molly Tenbrook, and I want to thank you all for joining us today for our webinar. Before we jump in, I'd like to give you a brief introduction to TriLogic and what we do. For over 30 years, TriLogic has provided software and services enabling engineering groups to design, develop, and deliver products through excellent support, training, and consulting services to help you achieve success sooner. Oasis Sales has been a mentor premier partner for over 16 years. Their industry knowledge and experience make them uniquely qualified to understand your business and how technology will make their customers successful. As you can see highlighted here on the map are the regions that each Oasis and TriLogic cover. Here you can see the different design and product management areas that TriLogic covers. You'll notice that we have tried to create a suite of products that will provide a front-to-back solutions all the way from concept to end of life. And now just a couple of housekeeping items. You can open and close your control panel with the small arrow at the top on the left. There are two ways you can join the audio. You can either join with your microphone and speakers or your telephone. The instructions, if you wish to switch, are in the audio section of the control panel. Today's presentation is being recorded and should be available within 48 hours. All participants will be in listen-only mode during the presentation. Please submit your questions in the question panel in the GoToWebinar control panel. And now I would like to introduce our presenter for today, Walter Goody. Walter has over 25 years of experience in ASIC and FPGA design and holds an MS in electrical engineering from Washington University in St. Louis. He worked for over 6 years doing ASIC design at Tellabs Operations. From there, he went to work for Mentor Consulting, where he consulted on various ASIC projects, including time spent in München, Germany, and Helsinki, Finland. For the last decade, Walter has worked as an application engineer supporting Mentor's line of functional verification projects. Please welcome Walter.
Thank you. Today's webinar is going to be an overview of a couple of Mentor's formal technologies. So we're going to go over Questa Autocheck and Questa CDC. So if you think about, today's FPGA verification, Moore's law continues to apply. We continue to double the size of these FPGAs every 18 months. And so we're now looking at 2, 3, 5 million gates on an FPGA. And so the FPGA world is starting to see some ASIC-like challenges. In the ASIC world, it's always been very important to fully verify your device because it was very expensive to respin. Well, the ASIC world, what's happening now is because of these higher densities, because of how complicated the ASICs are getting, it doesn't cost you $1 million, but it might cost you days, weeks, months to fix problems, to find things in the lab, to find a problem once it gets into the field. So we are starting to see that a lot of companies with the FPGAs are starting to adopt more ASIC-like verification. So, one of the things we find is that just doing simulation, RTL simulation, is, becoming more inefficient. And, this is an example of how that, why that is. So even for a simple circuit like this, it's a 2-bus comparator, and it's just comparing whether bus A and bus E are equal, and it puts out a 1 if they're equal, it puts out a 0 if they're not. To simulate this fully would take every possible combination of A and every possible combination of B placed on these buses. That's 2 to the 64th different combinations you'd have to put on those buses. So even with a really fast simulator, you're virtually never going to simulate all that. And so what we do instead is we put a representative set of values on there, maybe all zeros, max value, do some kind of walking patterns, and then we can say with a pretty high degree of certainty, but we can't prove it. So the Questa formal verification tools, what they can do is they can take this circuit, and then we can make an assertion about that circuit. So we're saying whenever A equals B, E is a 1. And maybe we make another assertion that says when A does not equal B, E equals 0. So those two assertions, and we give those to a formal verification tool, and it can pretty instantly tell us, here are the two values that you put on there, and you would have a violation of one of those assertions. So in this case, that would happen instantly because this is a fully combinational circuit, and what we're doing is basically a mathematical proof. Once we start adding registers to the picture, now your design has state space and state memory. And so again, simulation, what we're doing to that circuit is we're sending a set of stimulus through this design, and we're hoping that that stimulus will maybe uncover some errors within my design. Formal verification is doing the opposite. What it's doing is taking that circuit, taking these assertions that we've made about that circuit, and it's calculating every possible state my design could get into and see if any of those states cause a error. And so what effectively that means is we are starting at some initial state, say reset, and we're calculating every possible state that we could go into a clock cycle after reset. And then every possible state we could get into from there, and from there, and from there, and from there. And so we're doing a full state space analysis, and we're doing a mathematical evaluation of all the logic within my design. And so it's basically, given this design, given this assertion, can I calculate a set of stimulus that causes a violation, or can I prove that I will never have that violation? And so that's basically what this static formal verification is calculating out this state space and either finding a counterproof, so showing you the stimulus that will cause it, or creating a proof that says there is no way that this circuit could violate that. And it's about finding this as quickly as possible before maybe you even have a test bench. So if you look at formal verification, back in the 90s when formal verification first started, these tools were very new, they were experimental. Writing those assertions, writing those proofs, writing those properties that I want to check, that was a really difficult task, and it required an expert in formal verification, probably somebody who has a PhD in this stuff, and it required a lot of effort. And what Mentor has done over the last couple of decades is we've taken those formal engines that calculate that state space, that do this analysis, and we've automated a lot of the properties that we're checking around it. So we've tried to package a set of properties that you don't have to write. You just get to use that formal engine with those properties. We've packaged those into formal applications. So they are specifically targeted problems, are apps that target specific problems, have very little user input as far as creating the assertions go, but they use this formal engine to exhaustively solve problems that are hard to solve with simulation. So here's a look at the set of formal apps that Mentor has today, and we're going to focus on a couple of them. Autocheck will focus a lot of time on. This is just a set of properties that are good design practices that any good RTL should meet. So we'll talk about that. Once you own Autocheck, then you can start to add some of these other applications. Cover check is about, I'm trying to do code coverage. I have uncovered code. Is that code reachable? Am I going to waste a bunch of time trying to cover that code? If it is reachable, it'll show you the stimulus to get there. If it's not, it'll tell you why. Secure check is basically for if you have protected data within your system, you think there's only one or two ways to access maybe these encryption keys. What secure check does is it's a set of properties built in that you say, this is the path that I believe that you need to follow to get to this information. Are there any backdoor paths that I don't know about? Property checking is you have that formal person write these properties, although even there we have some automation of creating those formal properties a little bit. So that's kind of the traditional formal property checking applications. And then we've taken that same engine and we've turned it to the clock domain crossing problem. So what this does is it finds all the clock domain crossings within your design. It analyzes whether or not you have synchronizers, whether they're appropriate synchronizers, and then uses the formal state space analysis to see whether or not you can violate the timing required by the synchronizers that are in place. So that's Questa CDC. To do the simulation, and I'll talk about something called Reconvergence a little bit later, that uses what's called a CDC Effects engine. So when you buy Questa CDC, you get one of these engines. And then we've started to introduce some other add-ons to the base CDC solution. The first pass, the static CDC and all this happens at the RTL level. There is, a argument for reapplying this analysis at the gate level to make sure that your synthesis and place and route tools did not re-optimize logic and introduce CDC issues that were not in the original RTL. So that's the CDC gate level add-on. We've also started to see as resets have gotten more complex, that just like clock domain crossing, reset domain crossing has become an issue. And then more for the ASIC world, when you're doing power gating and turning off the power to certain areas in your design, that can introduce CDC effects as you power down and power up different areas. So these are all pieces of the puzzle. I'll really focus on the CDC problem. So one of the things I just want to point out right away is that Mentor sponsors this website called the Verification Academy. The Verification Academy is like three things. It's a set of courses on different verification topics. That's probably one of the main uses. There are cookbooks for doing functional coverage and for UVM test bench. So those are more or less online references for understanding and creating coverage and UVM test benches. And then finally, there is online forums where you can ask questions of our verification experts. So I just wanted to point out a couple of the courses. We have some formal verification technology courses that just kind of introduce you to the concepts. Then we have, a few other courses on assertion-based verification, on our automated formal solutions, and then, some that are directed towards CDC and some other things. So in summary, our Questa formal is formal property checking that is a complementary technology to simulation. It's able to solve problems that are really difficult in simulation. It turns out that formal methods really do complement, and the things that are hard to solve in simulation are relatively easy to solve with formal tools. Questa Formal has a lot of powerful capabilities. We've automated most of those into some automated apps. So first of all, I'll talk about the Autocheck app. So Questa Autocheck is basically directed at the RTL designer's dilemma. The RTL designer is designing his code and wants to make sure there are as few errors as possible found as early as possible. So even just, you could use some assertion-based verification techniques, but even there you need to create a test bench. If you look at the time spent on debugging, on verifying, there's a lot of time that's spent developing a test bench, creating and running tests, and then debugging those. That's where most of that time is spent, and Autocheck is basically meant to be something that you can apply to your RTL code as you're creating it. You can start to wring out some of the common bugs in RTL before you ever have a test bench. And so basically what you do is you take your RTL, you use the same compile scripts that you would use to run simulation. Those are the front-end compile that you do to do this Autocheck, and you basically, maybe name a few clocks, name what the reset is, and if there's any maybe tied off inputs or something, you push go, and it does a whole set of checks, probably about 3 or 4 dozen different checks that it does. So it's very push button, it's very fast, it has exhaustive results, and it's finding bugs as quickly as possible. And so you don't need a test bench. You're not writing any assertions. They're all prepackaged with the tool. And it finds things that are static, like combinational loops and other things that you might find with a linting type tool. But it also adds, because it's assertion based, it adds a temporal aspect to it. So it's able to look at what happens over time as you're clocking through your design. And so it will find temporal issues, and if it does, it will generate timing diagrams that show if you apply this stimulus, this will uncover this, bug in your design. So it's easy to use, it's push button, there's no test bench required, finds bugs very early, and we think that it saves a lot of time, and it really automatically improves your design quality. It finds bugs that linting tools may miss because of 2 things. One, because of the ability to do these temporal state space analysis, and 2, it takes into account circuitry surrounding certain blocks in your design. And so it's got a higher signal to noise ratio. It will find bugs that linting won't find, and it will clear things that a linter might say, hey, you need to look at this, and you'd spend a bunch of time realizing that, due to the environment this lives in, that's actually not a problem. So less false negatives, less false positives. So what kind of things does it find? Uninitialized logic, X propagation, combinational loops, arithmetic checks, bus checks, FSM checks. So basically you take your RTL, you push go, the tool actually does like kind of a first pass formal synthesis, comes up with this formal net list, and then does all of these different checks for you. So the first pass through, you will see it will find a bunch of things. You could have violations, you could have warnings, you could have, or cautions we call them. And every one of those has a status to start with. They're all uninspected when it runs through the tool the first time. So then you can go through and you can say, okay, this is a bug I need to fix. This is something that I think I've already fixed. This is something that we're waiving for whatever reason. So you can put the status on there, and then in subsequent runs, those statuses that you put on there are reapplied at each point. So how does this differ from a linting tool? It does a lot of, complementary things, but linters are rule-based and they're static. So they're checking the semantics and the syntax and the static view of the design based on static rules. There is also, in most linters, there's some design style, so you can have things like naming conventions and some other things. So we do not do those naming convention checks within Autocheck, but we do the syntax checking, obviously, and the statics checks, but most of our designs are based on assertions, which means instead of static, assertions by their nature can check temporal aspects of your design. This bus, should have a handshake, and, there is some, when I see this, 5 clock cycles later, I should see this, and then I should see this, and this. And so because Autocheck is based on assertions, it adds that temporal checking so that it's not just a static view of your design, but it can find problems due to timing in addition. So it's doing the sequential analysis using functional engines. It creates functional coverage reports, and it has a really rich debug environment. So how is this possible? What are the things that this does that a linter doesn't do? And so if a linter looked at this code, this case statement, it would say, okay, everything looks fine with this case statement because, this is the state machine it's seeing. But what a Autocheck would be able to do is not only is it looking just at this case statement, but it's looking at the sequential logic that's driving the inputs to this case statement. And for whatever reason, let's say it finds that when that state machine is in this 100 state, this signal sig is always going to be a 0, which means that this is actually a deadlock state that a linter would notice, but you would not see because, with a linter, but our Autocheck tool, because it's looking at the surrounding logic and doing this deeper sequential analysis, would find things like that. So, we're creating, as I said, this formal model of our design. We're running it through a bunch of different formal engines. If you're a kind of formal technology geek, you'll understand that this sequential behavior allows us to find, issues that are due to timing or due to surrounding logic. It finds corner cases and then allows you to maybe put in some optional things. So let's take a little closer look at some of the things that it might be doing. So arithmetic checks. If I have arithmetic expressions in my code, it will analyze and say, you've got this divide in here, and I can see a case where you're going to do a divide by 0. Or, I see that you have 16-bit buses defined, and I can see right here that this code is going to cause an overflow, and you're going to overflow and get a 17th bit because of this multiplication you've done, and it will warn you that you're having bus overflows. Bus drivers, it will be able to detect if you're ever going to have multiple drivers. Other things like if you have array indexing. So let's say I have an array that I've defined from 0 to 1024, and it will be able to analyze my circuit and say, the address bus that you've put in here, you've only defined 0 to 1023, and I can see that we could generate an address of 1522. And so you're going to be having out of bounds array addressing, things like that. As I kind of said, it will find these issues, and then if it's timing type issues, it will generate timing diagrams. If I have state machine issues like deadlock code, live lock code, things like that, it will generate a state diagram, and it will flag why we have this issue. So it'll say, you know, I'm going to get deadlocked in this read state because the condition that causes me to branch out, none of these three conditions will ever be met when I'm in that read state. So things like deadlock code that once I get into it, I'll never get out of. So that's for state machines or other issues. Unreachable code. If it is combinatorial, you know, here it's combinatorial feedback loops, but if it's structural issues in my code, we'll generate schematics that display what the issue are. And, you know, you click on that, you say, show me what this issue is, and it will bring up that structural schematic. So other kind of checks that it does are, you know, register checks, so multiply driven or stuck at, clock as data, undriven logic, illegal ranges I talked about. And so just, I think there's about 50 to 60 different assertions that are built into this tool, and it helps you to find issues with your code before you have a test bench. So you can kind of, before you check in any code, maybe you do revision control, you run it through AutoCheck, and it flags a few errors. You go fix those before you check things in. So a lot of our customers, what they do when they own AutoCheck is they use it to harden their RTL code before they ever run any simulations on it. So that's AutoCheck. So now let's look at the clock domain crossing problem. So right here is from a set of surveys that we do every couple of years. Strangely, as we're speaking right now, the 2018 version of this survey that we do is being presented internally at Mentor, so I'll have to look at that. But, you know, I expect to see that this trend is continuing, that even in the FPGA world, we're looking at an average of 3 or 4 clock domains, and we, you know, have 20 to 30 are not uncommon. I believe the 2018 data is showing that we're getting even more clock domains. And then if you look at why FPGAs are respun, meaning basically why do we have to go back from lab testing back to the, you know, to the environment, the number one reason continues to be functional or logical errors. So the code is not written correctly, and I've got to correct the logic. But the number 2 reason continues, and I expect this trend to be, you know, uptrending, is clocking issues. And so that is either asynchronous clock domain crossings or buffering or something. So what is asynchronous clock domain crossing? I mean, hopefully all of you know what clock domain crossing is, but if I have sets of logic and registers that are clocked by 2 different clocks, and those clocks are coming from different timing sources. So clock domain A and clock domain B, they might even both be nominally, say, 10 megahertz, but if they are derived from different timing sources, that means they have some slight difference, and you will see that they will be moving, the clock edges will be drifting with respect to one another, and eventually you're going to get a TX that comes over here and it hits the setup and hold window of this register. And that is basically what is metastability. So metastability means that you hit that setup and hold window, and the signal, the Q output of that flip-flop is going to ring. And so you have the metastability events, and you don't know whether the signal is going to settle out to a 0 or a 1, or possibly even continue to ring forever, potentially. So setup and hold violations cause metastability. So that's kind of the scientific way to say it. The best way I find to explain metastability is you are driving down the street, you are coming up to a traffic signal that is currently green, and there is always that zone where somewhere that signal is going to turn from green to yellow, and you're just far enough back from that intersection that you can't decide whether you should hit the gas and blow through or hit the brakes and stop. And, you know, a lot of people say to me, well, I always hit the brake. Well, okay, you're a fast flip-flop. Move 25 feet further down the road, and you are eventually going to hit that setup and hold window, that metastability window. So how do we deal with metastability? We deal with metastability by putting in some kind of synchronizer. So for a single bit of data, all we really have to do is put in 2 flip-flops in a row. And so what happens is when this signal right here hits that setup and hold violation, Q goes metastable. And let's say that happens about once an hour based on, you know, what the clock speeds and what technology I have and all this. So once an hour, I would have a metastable effect on Q. If I just put a second flip-flop right here, this RX data is going to go metastable about once every 100,000 years. So you're basically going to remove that possibility. So here's where that setup and hold violation happens. Right here, I have this metastable event. This Q goes metastable. I don't know whether it's going to settle to a 0 or a 1 or continue ringing. At RX data, what happens is I'm pretty confident this is never going to go metastable, but what I don't know is from this moment, is it going to take me 1 or 2 clock cycles for that 1 to show up over here on the RX? So I'm kind of trading a unpredictable value for an unpredictable delay. And that's essentially what happens with almost any synchronizer structure. So for a simple synchronizer, like a 1-bit synchronizer, even this has a timing requirement. And what is that timing requirement? Well, if this clock domain is, say, 10 megahertz, and this clock domain is 5 megahertz, that means potentially I could put a 1 on TX data and then put a 0. So that 1, that pulse would come and go before I ever detected it over here with clock domain B. So I have a timing requirement that says the data rate of TX data has to be less than or equal to the clock rate of my receiving domain. So even this simple 2-bit synchronizer has a timing protocol. For buses, you have to get a little more complicated, and then the timing protocol becomes more complicated as well. So if I look at a CDC detection tool, it's got to do 3 things. First of all, it has to analyze all my clock domain crossings and make sure that I have synchronizers. A lot of tools on the market will do this first step. The second thing it has to do is say, have I violated the timing protocol of this synchronizer? Is it even possible for my circuit to violate this timing protocol? That becomes a little trickier. Not as many tools do a good job of that. And then there's a third thing that you need to think about. And that's, let's say I've done the analysis on this path. I have a correct synchronizer. I definitely cannot violate the timing protocol. So this signal getting over to here is correctly synchronized. No issues here. Now let's look at this path. I do the same analysis. I have a correct synchronizer. I cannot violate the timing protocol. So this path is good. But over here in clock domain A, let's say these 2 signals, they got generated on the same clock edge. I've now gone through this synchronizer, and on the outside of that, this signal could be plus or minus 1 cycle off from this one. So while these were generated on the same clock edge out of over here, they can be skewed plus or minus 1 clock here. Now, if I go through my logic cones and maybe even go through some sequential logic or some registers, when I get down to here and I get to this combinational logic cone, is there an assumption that these two signals are in sync with each other because they were when I generated them, but they are actually now out of sync by one cycle? And that's what's called reconvergence issues. So does my logic account for the fact that these signals that were generated in sync are now out of sync with each other? So a good CDC tool needs to do all three of these things. It needs to provide a complete structural analysis of all the synchronizer structures, verify that they're there and they are appropriate. It needs to do a complete analysis of the timing protocol to make sure that there is no way we can violate that protocol. And then it needs to do a complete reconvergence analysis. And we do that by doing simulations where we find all the times when metastability can occur, and we inject jitter, basically. We inject different delays on those paths and make sure we've done a full study of those. A good tool is going to do an exhaustive, formal-based approach of analysis of all three of those steps. It's going to have a connection to your simulator so that you can do the reconvergence analysis. I haven't talked about this, but it's really nice to be able to do a hierarchical, scalable analysis. So to be able to do CDC checking at the block level and then take that analysis and include that at the chip level, because maybe the chip level, it's too much to do a full analysis. But if I can do block level analysis of my 4 blocks in my design and then bring that data together to do a full chip level, it allows me to, complete a chip level CDC analysis that would be impossible without this ability to do hierarchical. We want it to be low noise, so we don't want to be missing issues that are there, and we don't want to be flagging issues that don't actually exist. So that is the CDC solution that Mentor has. And one of the things that we're very proud of right now is that if you are in the automotive world, they have a body called the ISO 26262, and they do our certification of tools. And right now, every major simulator has been certified by the ISO 262, but Questa CDC is the only CDC checking tool that has gotten the ISO 262 compliance stamp. So that's something that, as I said, it's been about over a year and a half now, and no other CDC tool has gotten through the ISO 26262 qualification. We feel like what's driving the CDC is our high performance, our scalability to do block level to system level, et cetera. The fact that we probably have more CDC schemes, more synchronizer schemes than anybody else. We have then the ability to take our CDC analysis and bring your simulation test bench involved and even start to filter some of the questionable results even more by doing simulation. And then this all fits into the Mentor Unified Coverage Database so that you can bring it into your verification management solution. So our simulations create UCDBs, our formal tools create UCDBs. You can merge simulation and formal results together and, get a full thing. So we feel that we're accurate, we're scalable, and we give you really good debug guidance. So we are the only tool that currently has the ISO 262 certification. We have the most schemes. We are comprehensive. On the FPGA side, we are one of the few tools outside of the vendor tools that support FPGA devices. FPGAs have their own complication when it comes to running clock domain crossing checks. And so we have spent a lot of effort to make sure that we support all Xilinx, Intel, Microsemi, Lattice devices. And then just, one case study, we had a audio processing company creating a IC for doing audio processing. What they found was they had some issues in post-silicon. It was being very erratic. They tried a bunch of other CDC tools, and they were not finding issues. And they were incredibly impressed that we came in, and basically from the time we got the tool installed, within 90 minutes, we'd found several RTL design bugs, a bunch of problems with their design constraints that they had set up. And basically they said within 2 hours, they'd found a bunch of problems that they had not found using our biggest competitor, Spyglass. And they'd found 2 bugs using CDC within 90 minutes that had taken them months to find in the lab. So basically the workflow is you start with your RTL code, you compile it, you put in your design constraints, so your timing constraints on your clocks and your resets and any other things. If you have unified power format, that is for low power ASIC power gating, probably not a factor in the FPGA world. But you put those in, you run the analysis, and it spits out a full static analysis. You then review that static analysis. You will have multiple violations probably. You should hopefully have a whole bunch of proofs that say, we're sure you're not going to have any issues here. And then you have some caution, these yellow ones. And that says, we found some things that look okay from a static point of view, but we weren't able to completely prove, say, that you can't violate the protocol. And in that case, you're going to need to bring your test bench in and run some simulations that we can help you to refine the results. So as far as synchronizer schemes, as I said, we have, I think, over 50 built-in synchronizer schemes, and then the ability for you to create your own synchronizing schemes as well. So for instance, here's for a bus. If I want to get a 16-bit bus synchronized to a new clock domain, I can't just put 16 one-bit synchronizers on here, because the problem is for 1 or 2 cycles, I could have complete garbage on the output bus. So how do you synchronize a bus? Well, one way you do it is through this mux feedback approach. And so now what I do is I put the data that I want to send over, I hold it constant, and then I pass a control signal that says sample that data and then take the control signal away. And the idea is you pass that over, you sample the data, that goes away, and then now you're holding it in this feedback mux. So now I have a protocol. That protocol says I better hold this data constant for the entire time it takes for this control signal to go active and then go away in the received domain. And so maybe I do that static analysis and it comes out and says, this looks good, you structurally are okay, but I can't prove that you don't violate this timing. And so what the tool does is it generates a set of assertions that basically describe that protocol, that you have to hold data constant for the entire time that the synchronizer or the control signal gets synchronized. It generates those assertions. You run your simulation with Questa Sim. It collects coverage in there, and then either finds an example where you're violating that timing protocol, in which you get a firing that says you have a problem, or you run enough data and it collects enough coverage to say, I can now with confidence say you will never violate that protocol. And so that is the second step. So we do that static analysis, and you get a few things that have not been fully proven. And so from there, the static analysis generates those protocol assertions. And then we can use our formal state space analysis engine, or we can use our Questa simulation engine to continue to run those simulations, collect coverage, and then either promote or demote those cautions to failures or proofs. So that's kind of the whole process. And then the debugging is that we will show you these timing diagrams. If you have firings, we'll show you those. If we get proofs on the reconvergence side, whenever we find a potential reconvergence issue, we'll show you where that reconvergence issue is. We will go through and we will inject variable delays through those metastability paths and allow you to, collect enough information. One last thing I wanted to mention is that Xilinx now ships with Vivado. You can go into the Vivado Tickle store and you can download this Questa CDC button, basically, app. And what that does is within your Vivado project, you now have a Questa CDC button. If you push that, it generates all the scripts required to run Questa CDC analysis and launches Questa CDC. You still need to buy a license of Questa CDC from Mentor, but it automates the process of getting that project run in our CDC tools. The summary on Questa CDC is it is the most comprehensive clock domain crossing tool on the market. It is the industry standard for clock domain crossing, the only safety critical certified CDC tool on the market, and it has a proven track record for doing hierarchical analysis as well. So I have some stuff on reset check, but I only have about 10 minutes. And so I thought instead of doing that, what I would do is do a quick demo. But I did get one question that came in. What happens when RTL instantiates hard IP resources, such as multiplier memories? Can Autocheck make use of simulation files provided by the IP? So if you have hard IP from the vendor, we can't use simulation files. If it is encrypted RTL code, we are able to decrypt and at least do the analysis. We can't show you all the debug. If they're giving you just kind of behavioral models, then you're kind of left, as far as Autocheck goes, with just doing that analysis of the circuits surrounding, but we've kind of just black box those issues. So let me just show you real quick CDC. And I'm going to go over to the protocol analysis one here because we're running a little short on time. Make debug. So while I'm setting up this tutorial, if any other questions you have, go ahead and give them in. Hopefully everybody can see my Linux virtual machine here. So that's one thing I should mention is that currently Autocheck and CDC only run on Linux. We are in the midst of making a port to Windows right now, and we hope to have that Windows version of CDC and Autocheck by the end of the year. So the first thing you do is, you compile your code, and this is, I've already run it all, and I just wanted to show you some of the results. So the first thing I always look at is I look at the clocks, and you'll see that I have this analysis, and it says I have 3 clocks, and they've all been specified. So here's my directives for my clocks. So I said I have a clock input, clock in, which is 50 nanoseconds. Core clock is 60, Mac clock is 50. Now these are asynchronous to each other because I don't see that there's a clock group defined here. If I had defined clock group and I have 2 things that are in the same clock group, that means they may have different frequencies, but they're derived from the same source. So that will make them synchronous, not asynchronous clocks. So here you'll see I've defined clocks, and I see that I have 3 specified clocks, This tells me how many registers those are clocking. What I do like is that I don't see that there are any other inferred clocks, either primary inputs or internal clocks or whatever. So that's one thing you always want to make sure of, is to look at your clock thing and make sure that you have specified all the different clocks in your different sign. If you have inferred clocks, you're going to want to go back and add more constraints because you have other clocks that you didn't think of. In this design, let's go ahead and just look at the results here. So what you'll see is from my static analysis, I had a few violations. So this right here, it says there's combinational logic before the synchronizer. So let's take a look at that. And you'll see here's a register over here in the green clock domain and a synchronizer in the blue clock domain. But you'll see I actually have combinational logic here. And that is generally seen as an error. You really should go straight from a Q of clock domain A to the D input of clock domain B. Here is a similar thing where I have a green, I have, you know, some expressions here. And this, when I see this red, that means if I follow far enough back, I'm pretty sure I'm going to find some signals that are coming from another clock domain, and it must be here. Okay, there we go. So yeah, so you'll see I've got a green clock domain. I've got something that's coming from the blue clock domain going into this logic cloud, feeding a blue clock domain. So right there, when I combine signals from two different domains, I see them as red. So I knew there was some kind of an issue like that immediately. Now let's go back and see what other issues I might have in here. So I had some proofs. So if I look here, I'll see, okay, these were just some single bit synchronizers, and due to the timing of these two domains, if I went back and looked, I'd probably see that this is that 60 nanosecond domain, this is that 50 nanosecond domain. So I know that my data rate here will never exceed my clock rate here. Right here, I've got what's called evaluations. Now, evaluations, if I look at the structure here, this is one of the places where if you look at this, you'll see it looks like just a single bit. But if I go to the declaration of this, go to declaration, I'll see that's actually a bus. So why is it that I'm saying this synchronizer, that synchronizer is okay? Because I said before that I shouldn't be able to put 2-bit synchronizer or two flip-flop synchronizers on a bus because this could become problematic. Well, if I go back, and right here gives you a little clue, this is just a name that's put on here, but what the tool actually did is it looked at the data being fed to this D, and it realized that the data being fed here was gray-coded, so that only 1 bit of this bus is going to change on any one signal. And so instead of flagging this as an error, which most static tools would do, it was able to do that state space analysis, realize that this is gray-coded, and realize that this structure is actually okay, even though it's on a bus. So then I'll have maybe right here, view, yeah. Right here, I've got a couple of cautions. And the cautions are that I have what appears to be a good structure. So this is basically that mux feedback with an enable instead of a mux. I've passed it across, but it's cautioning me because it's saying, you know what, I haven't seen, I wasn't able to do a deep enough analysis to say that that's going to pass in that's never going to violate the timing protocol. So let me do one thing here. I'm going to bring up the simulation results real quickly. I think that's the one that I've done. Make. Actually, I think it was the Verilog version. Sorry. So I think I have these simulation results here. There we go. Yeah. So what I'll see here is I'll look at, this was the CDC checks I was looking at before that showed, the different violations and the cautions. And then right here, you'll see I had a simulation firing. So let's show. So what I'm seeing here is that I've run that simulation, and this is the data bus and the control signal that is passed to that clock domain B. And you can see while the sample signal is high, my data bus was changing, which is, going to be an issue that should never happen. So it's pointing out that that's a problem, and it demoted that caution to a issue. So anyway, that's a quick demo. I know we're running out of time on our hour here. I just wanted to check if there were any other questions on what we presented today. So kind of the summary is that we have Autocheck, we have CDC. These are both formal tools that allow you to do this analysis without a test bench, at least to start with the CDC, and will hopefully get you a better design with fewer problems. So one question that I do see came in is somebody asked, are these included with Questa Sim? And no, these are separate products. Autocheck is a product, Questa CDC is a separate product, and they are add-ons to do this formal analysis. I'll turn it back over to Molly if you have any final things to say.
Yeah, just if there's no more questions, thank you, Walter, and thank you everyone for attending.